Okay, so section 1.2. Now we're going to look at properties of e to the I theta. They tend to use a phi as opposed to a theta, but I like using a theta. Now they make a very good point of saying, e to the I theta is a notation. Now, I haven't really quite used it that way. So, for instance, one of the properties, their first property they give in proposition 1.3 is just something I used. And I used it to get the trig identity. Well, actually, to prove you use the trig identity. So, I kind of did it backward. So they say, well, e to the I theta 1 times e to the I theta 2 is equal to e to the I theta 1 plus theta 2. And you see, I just said, hey, that's true because that's how exponentials work. Well, actually at this point, as they point out, it's really just a notation. And so, if you're going to do a proof of this, what you really have to do is use the definition of what e to the I theta 1 and e to the I theta 2 are, which are these trig representations, cosine theta plus I, 1, I sine theta 1, and then times cosine theta 2 plus I sine theta 2. And so when I multiply these together, I get a cosine theta 1, cosine theta 2, plus, minus, minus because I times I is -1, sine theta 1, sine theta 2, and then plus I, and I have a sine theta 1 and a cosine theta 2 plus a sine theta 2 cosine theta 1, like that. And and so you see I need trig identities on both of those parts. And so this the real part there is cosine theta 1 plus theta 2, and then plus I sine theta 1 plus theta 2. I didn't really need that parenthesis there. Okay. And so that gets us to the e to the I theta 1 plus theta 2, like that. And so, that's, you actually use the trig identity at first to prove this property, but then, once you have that, you can sort of forget all those trig identities and redo them using the properties of exponentials. Okay, so that was property A. B, e to the I 0 equals 1. And these are all, if you know exponential functions, these are all pretty intuitive. C e to the negative I theta is equal to 1 over e to the I theta. D e to the I theta plus 2 pi is just e to the I theta. And let's see, absolute value of e to the I theta is always 1. And again, that comes, we know this polar form, the modulus goes out front. Well, the modulus is 1 on this, so should be 1. And then f, the derivative of e to the I theta with respect to theta, well, it's just a chain rule, so you get e to the I theta, but then times the derivative of I theta, which would be I, and so you get I e to the I theta. And in the text, they actually do the proof of that one. Again, they just go to the cosine. So, the whole point is that they're saying at this point, this is just a notation. What you're truly working with are the cosines and sines like that. And so now, okay, derivative of the cosine is minus sine. So this is minus sine theta plus I cosine theta, like that. Of course, when you look at that, you kind of go, that doesn't look like what I need. I need a, because in order to do this, I need a I sine theta and I need a cosine theta. So if I multiply well, actually, not multiply. I'll factor out an I. That's the way to talk about it. Factor out an I. This will be I. Now, here, what I have left is cosine theta. Now here, factoring out an I, well, -1, remember, is I times I. And so this is plus I sine theta. So this is I e to the I theta. So there you go. There's our proof. And then finally, with these properties, we just get this definition of a root of unity. And a root of unity is simply any number. Okay, any number of the form e to the 2 pi I m over n. And the idea is, notice that if I raise, make that z, if I raise z to the n, I get e to the 2 pi m I all over n to the n, but the n's now cancel using properties of exponents. So this is e to the 2 pi m I. And so you see that's just a multiple of 2 pi, and so we get 1. And so that's why it's called a root of unity. We have z to the n equals 1. And so, if I wanted the fourth root of unity, they would be e to the 2 pi I 0 over 4, e to the 2 pi I 1 over 4, e to the 2 pi I 2 over 4 and e to the 2 pi I 3 over 4. Okay, and if I raise all those to the fourth power, I get 1. And in this case, this actually is the number 1 right here. Then the second one is the number I. Hang on. Let me pause it here. Grandson came in again. Okay, so we get I for that second one. And then we get -1 for the third one. And finally, for the fourth one, we get -I. Okay, and again, that's just looking at our circle, and see here would be theta equals 0. Up here is theta equal pi over 2. And here is theta equal pi. And here is theta equal 3 pi over 2. And so those are our 4 roots of unity. Now, actually, from this one, we get, we had Euler's formula, but now we also have Euler's identity is what it's called. And that would be e to the I pi is equal to -1. Which, that's a really cool identity just from a number theory point of view, because it's got, it's got the number e, which is very special. It's got the number I, which is very special. It's got pi, which is very special. And it's got -1, which is very special. And we could even rewrite it slightly differently. Now, it wouldn't have a -1 in this case. Well, I guess we could still write it as a -1. But if you move it over, e to the I pi plus 1 equals 0, we can toss in 0 to the mix. And if you really wanted that -1, I guess you could write it as e to the I pi minus a -1 equals 0. So there we've got, e I pi -1 and 0 all put together in one identity. Pretty awesome from a number theory point of view. Okay, so that's properties of this exponential or really polar form. Again, we tend to just call it the polar form because where I got to go back here. Right there. E to the I theta really at this point is just a notation. And so it's just a shorthand way of writing the cosine theta plus I sine theta. So technically, it's just a notation. However, it really does have all these properties, and in chapter 3, we'll visit the exponential function, the complex exponential function, and certainly we, I theta, if we just think of theta as some number, then that is just a complex number, and we could call it z, so we could call this e to the z. It just happens to be a pure imaginary number. Okay, so that does it for, I think, everything in section 1.2.